Okay, so Chapter 9 was all about one sample hypothesis testing, and Chapter 10 is all about two sample hypothesis tests. So for example, you might want to know if the proportion of defective parts coming off a machine is different for the old machine versus the new machine. So you would need to get a sample from the old machine and a sample from the new machine and compare the probability of a defective part or proportion of defects. Or let's say you want to compare the average salary of an employee at Google versus Amazon. Notice you'd have to take a group from Amazon and a group from Google, so two independent separate groups, and then compare the average salary. Okay, so for two sample tests, we're talking about two different groups of people. The groups are comprised of different individuals so that the two samples are independent of each other. This chapter also talks about dependent samples, but that's going to be an optional reading for this class. Okay, so we'll just stick with independent groups. You do need to figure out first whether you have independent groups or dependent groups, but basically independent groups is going to be two different sets of people. If I wanted to compare old machine to new machine, I need to get a sample from the old machine and a sample from the new machine, so I have two independent groups. If I'm comparing GPA of juniors and seniors, one group has to come from juniors and one group has to come from seniors, so those are two independent groups. You can think of an example where one group is taking a placebo and the other group is taking an experimental new drug. You wouldn't want the same group of people taking both because they may have just different effects, and those people are thinking to themselves, wait a minute, why am I taking two different medications here? Okay, so the book starts with means, but I'm going to start with proportions because it's just a little easier to set the foundation for the rest of the chapter material. Okay, and just like Chapter 9, we're going to have a null and an alternate hypothesis. The null, just like Chapter 9, is always going to have the equal sign. So basically for proportion problems, your null is that the proportions are equal. There's no difference in the proportions of defective parts coming off the old machine and defective parts coming off the new machine. No difference in average salary of one company versus another. And also, just like Chapter 9, the claim or the alternate hypothesis will have either the not equal to sign, the less than sign, or the greater than sign. So basically I'm saying here, old machine is different from or not equal to the new machine. So maybe trying to prove that there is a difference between the old machine and new machine. Or if I'm talking about defective parts, then I would hope that the new machine would have fewer defective parts. So the old machine, if that's proportion 1, the old machine should be greater than proportion 2, the new machine. Okay, so order matters here. Be careful with the sign. If a problem says errors have gone down, it's not necessarily a less than problem because the order matters. If the before is greater than the after, then you have a greater than problem, but it still has gone down. But we'll see that when we get into some problems. Okay, another way you can write it, which you'll see in the book, is basically like this. Proportion 1 minus proportion 2 equals 0, or is less than 0, or is greater than 0. There's going to be no difference in the end result, and I think it's a little easier to think in terms of proportion of before is less than the proportion of after, or proportion of defects on the old machine is greater than the proportion of defects on the new machine. Okay, so either way you do it, you're going to come up with the same answer and the same sign, either not equal to, less than, or greater than. And a little detail on that is in the notes pages, but you don't need to know that for the quiz. Okay, so again, it doesn't matter which way you write it, the sign will be the same and the result will be the same. Okay, so let's look at a problem. We saw something like this in Chapter 9, where we wanted to know if the proportion of people buying a Dell went up from a specified number, 45%. This problem, we're basically saying, okay, let's look at the before and the after and compare the before and after. So now we have two proportions that we're comparing. So does Dell's new design strategy work? A sample of 200 people before the strategy resulted in 90 saying they would buy a Dell. After the strategy, 50 were polled and 30 said they would buy Dell. I want a 5% level of significance, what do you conclude? Either evidence that the strategy works or no evidence that the strategy works. Okay, so let's take a deeper look at this problem. Notice that I have the before and after terminology in there. So that's an indication that this is a two-sample problem, a chapter 10 type problem. Notice also that I have 90 out of 200 and then 30 out of 50. Okay, that's an indication this is a proportion problem, not a mean or average problem. And so I basically have 90 out of 200 before and then 30 out of 50 after. Okay, so in setting up the hypotheses, I know the null always has the equals. Basically the null is going to say that there's no difference. The claim is that the strategy works, which means the proportion after should be greater than the proportion before. So if we're putting it in order of before and then after, you would actually have a less than sign. Okay, so the order before and after, before should be less than after. Okay, I could switch it and put the after first, but then I would have to switch the sign to less than. Or I'm sorry, greater than. Because the proportion buying Adele after the strategy should be greater than the before. Okay, so let's take a look at that a little deeper. We still have the same steps as chapter 9, set up the hypotheses. If the strategy works, then the percent before should be smaller than the percent after. So again, I'm just going to emphasize that a lot because it's something that students struggle with sometimes. The order matters. If you're putting the before first, then that should be smaller than the after. So you would think maybe it's a greater than problem because you're trying to see if the proportion went up. But what you want to really know, what you really have is a less than problem because before should be less than after. Okay, so we're claiming that before, the proportion before is less than the proportion after. Basically it went up, so the point goes to the smaller one and the mouth goes to the bigger one. After should be a greater proportion than before, which means our null is either the greater than or equal to, or you can just use the equal sign, just like chapter 9. Okay, so let's look at what we have. For sample 1, we have a sample of 290 of them said they would purchase Adele. So in this book, they use p hat for the sample proportion, so that would be 0.45. And after, we've got 30 out of 50, so that's about 60%. So even though we see that 60% is in fact greater than 45%, we can't conclude that that proportion is greater, that the proportion went up, because we don't know if it's statistically significant. Okay, step 2, enter the data. I'm going to go to hypothesis test just like chapter 9. And remember in chapter 9 we did mean versus a hypothesized value. So basically, has the number gone up from 45%? And we also did proportion versus hypothesized value. So that would be the, has it gone up from 45%? Mean versus hypothesized value, has the average gone up from 60 minutes or something like that? Okay, so we've done this one in chapter 9, we've done this one in chapter 9, and chapter 10 we're going to be doing 2 independent proportions and 2 independent groups. Okay, so here's what you have. Notice the default has you entering the sample proportion. However, you can enter an X value, like, we had 30 out of 50, so you could put the 30 there, and since it's not a point something, it knows to turn it into an X and actually calculate the 30 over 50 for you. Okay, so group 1 is going to be my before, 90 over 200. Group 2 is going to be my after, so 30 out of 50. And I'm assuming that group 1 should be less than group 2 because the proportion should have gone up, so group 2 should be greater than group 1. Okay, remember the point will go towards what I think is the smaller number. For this class, you're only going to do a hypothesized difference of 0. It's not quite as common to actually choose a hypothesized difference. I'm not saying that, oh, it's gone up by 10%. I'm just wanting to know if it's statistically significantly higher for group 2. And we can keep the confidence level at 95. Okay, notice the small p for proportion changed to x because we didn't enter a proportion. So for this type of problem, I'm given x and n, the number of people out of 200 So I don't have to type in the 0.45 or the 0.6. I can just do the 90 out of 200 and the 30 out of 50. And notice also we want less than because the before data should be less than the after. Again, if I'm choosing the after to go first, then I would just switch the sign. The point goes towards what you think is the smaller number, and the wide part of the sign goes towards the bigger number. Okay, so I've put the sign in there. I'm assuming before is less than after, and my sample information. So step 3, just like chapter 9, the final result is based on this rule. If the p-value is less than alpha, reject the null and support the claim. If the p-value is not less than alpha, then basically you have to go with the null because you're not finding evidence for the claim. Okay, so let's go back to the problem. Does Dell's new strategy work? 90 out of 200, is that less than 30 out of 50? Is it statistically significantly less than? And if we find that it is, then we have evidence that the strategy works. So basically, if we can reject the null, that there's no difference, then we do have evidence that the strategy works. So we would choose A if we reject the null. If we can't reject the null, then we choose B. Here's what we get for the output in Megastat. You'll notice the p-value is 0.0288, and it has, the other information there, the 0.45 for the first group, the 0.6 for the second group. Okay. So the p-value is less than 0.05, which is our alpha, so we can reject the null and support the claim. So basically the proportion did go up, so that means that the new designs worked. The before was significantly less, the 0.45 was significantly less than the 0.6. And that z-score is the test statistic, which you'll need for some of the homework problems, but what I'm more concerned about is you getting the p-value and making that final conclusion so that you can make, do the interpretation and make decisions based on it. Okay, let's do another problem. Is CU significantly more selective than University of Colorado, Colorado Springs? A lower percentage means more selective, right? If I accept less people, then I would expect to be more selective. So we're trying to show that the proportion for CU is less than the proportion for UCCS. They're more selective, which means they have a lower percentage acceptance rate. So the null is that they're equal to or greater than. Okay, and I got data from a website about the acceptance rates. Acceptance rate for CU is 87.7%, and the sample size was 22,500. So you can easily find the number of accepted by just taking, you've got that percentage, and that equals x over 22,500, so you can solve for x. Or you can just enter the proportion into Megastat. All Megastat needs is the proportion and the sample size. Okay, but if you did the calculation, x would be 19,732.5. So 19,732.5 divided by 22,500 is the 87.7%. For UCCS, it's 91%, and the sample size is 7,030. So that means they accepted 6,397.3. Okay, so now we can see that in Megastat. Again, hypothesis test, comparing two independent proportions. Enter the sample proportion you want to enter. You want to enter 0.877, not 87.7. And 0.91 for UCCS. Hypothesized difference is always going to be 0 for this class. We just want to know if there's a difference. We're not saying, is the difference 10% or is the difference 2%? And since we're putting CU first, we would expect CU to be less than UCCS. So group 1 less than group 2, because more selective, lower acceptance rate. Okay, so notice sometimes you'll get something like this for the p-value. That's negative exponent 14, so basically 0.00, 14 zeros. So basically something like that is close to 0. The test statistic is negative 7.57, so you'll also tend to see higher test statistics for lower p-values. But again, that z-score, that test statistic, just need to know for a couple of homework problems. You won't need to know that for the quiz. That z-score basically just helps you find the p-value. So I'm more concerned with you knowing the p-value and making the final conclusion. So since it's close to 0, the p-value, it's less than alpha. In fact, it's less than any common alpha we would have. So we reject the null and support the claim that CU does have a lower acceptance rate than UCCS. So they are more selective. Okay. I think it's helpful to actually write out your hypotheses, and that way, you know, once you can either reject or not reject, you can cross one off and circle the other, and then it's a little easier to make the interpretation. Okay, p-value is close to 0, so we reject the null and support the claim that CU is more selective than UCCS. In other words, CU's acceptance rate is statistically significantly lower than that for UCCS. And one reason it was so significant is, remember how large our sample sizes were? So even a small difference is going to be statistically significant because of those huge sample sizes. Okay, so let's look at a couple of other examples.